So today's topic is about systems, how to describe the digital systems on the MATLAB. And basically, first, let's take a quick look at what kind of things are we doing today. So on the exercise, there are these questions about linearity. Linearity, causality, time shift invariance, and then there's also the fourth property, which is the stability. I leave the stability for the for later on. And basically, we have flow charts or block diagrams, how to describe the system parameters from the flow chart, calculating zeros and poles, determining the system parameters for a system described as state. Another difference equation, calculating again zeros and poles, creating a sound sample, and then basically running that sound sample through a system which is described in here. Okay, but let's start from the beginning, which is the stability and stuff. Okay, so the linearity, there's a hint. If a system is linear, then basically a couple of things are true. It's commutative and additive, meaning that if you have a system F, okay, let me do it by a block diagram. So system F, which does something for input X, so basically if a system is linear, if you replace that by some scaling factor A times x1 n plus b times x2n, so the input signal is a combination of different signals, and they are even scaled with arbitrary numbers. What should come out is actually, well, for xn it would be like this, but for that input you should get A times f x1n plus b times f x2n. So that's basically the definition of a linear system. So input, for this input you should get that output, meaning that you can actually take the scaling factor outside of this. And if there is a sum of signals, you can break the sum. Okay, good. So that's the linearity. And we can test it. Should we test it immediately? Yes, we can test it. Let me start the MATLAB and see if I can actually, oops, just a moment. Where is my MATLAB? Well, it takes for a while to start up. So anyways, what we can do on the MATLAB, we actually make a function which basically does the whatever this is supposed to do, and then call it call it, there we go, call it with arbitrary, meaning random vector and another random vector, and then basically have two random numbers, so arbitrary numbers here. And then put this one inside of the formula, calculate the when the system input is there. So basically this function calculates a times x1n plus b times x2n. Okay, and then basically you just compare if these left-hand side and right-hand side are the same. So this is a brute force kind of test. It does not prove the if the system is really linear, but it basically, if it's non-linear system, you can see it immediately. So it's kind of brute force kind of engineering proof. Don't show that one to mathematics teacher. He will kill you. So, but this is the nice thing about the computational things. You can test things quickly, and then if you are really into it, you can start drawing scribbles on the paper and try to find it, you know, on a really proving way. So brute force test. Brute force test for linearity. So basically test if a times x1n plus b times x2n is same as a times f x1n plus b times f x2n. Okay, good. And we will do it in a way that I will make a new function, for example, my func1, and by default it starts the editor with the well, my func1.m file name. So m files, have you made the m files? Scripts or functions? Scripts. Okay, scripting is easy. When you get something done good on your command editor, command line, then you just copy paste that one to script. Now you are done. The functions are actually quite simple, but these are similar functions to, say, C programming language. You have to define it as function by saying, well, the following is a function. And then you define the output. Okay, for example, y equals, and then the function name, my func1, or something more descriptive. And it has one input. Yes, just like here. Whatever comes in, there's only one input for the block. Okay. And then whatever you need to do, you will just have this one and do whatever the system is supposed to do. And basically, that's the good prototype for the any one single input and single output system, SISO system. Okay, What you can actually put here next is a command line like that, and then the function description. And maybe a author name there. And date. This is April 17, 2018. And copyright notice, basically. So the similar things what you do on any program if you want to claim them your own. Okay, and then if you have a empty line here, then this comment does not show on help. Okay, what I'm talking about here? Strange. Let me go to my MATLAB window, since now I can call that function and say help my func1. So whatever you write on this comment section on the beginning will show up as help. So that's how MATLAB help actually works. Okay, and let's not make it too hard. So here you have all the calculations required, and at some point you'll set the value for y. All of these values inside a function, including the input variable and output variable, are actually kind of local variables here. And the return value is the y. So you will use it as any other function. You set a variable equals to my func1 with the input variables. Okay, so just to prove a point, I'll just make a simple function that multiplies the input by number 2. Whoa. And save. And then call it. So if I call this function with just for number 1, it gives me 1. If I actually call it with a vector 1, 2, 3, it multiplies those. So basically it just does whatever you have on the input, it does whatever you have on inside of the function. Good. So now we have a basically something to test the linearity. If is the system 2 times x linear? So that's the simple system. In the exercise, there are actually 4 systems. So you need to make 4 different functions that return those values. The 4th one is a little bit tricky, since this is a single input system. So you have just xn coming in, and then you multiply it with n. Where do you get the n? Well, you get it inside of this function. It cannot come from outside. It must be inside. Okay, so basically on the exercise you will do this test for all of those 4 functions. Okay, good. So now the test itself. So basically first we generate the test vectors and scalars A and B. A, B. Okay. So, whoops, now I'm messing up here. Setting up my system. Okay, so for example, a scaling factor could be rand n and just one value of one random value. Yeah, that'll do. You will probably get exactly the same number. That's because the MATLAB random number generator starts with the seed number of 0 every time you start it. You can randomize also that, but anyways, when you start the random number generator, it always starts from the same seed number. That's why you would get exactly the same random numbers. So the question is, are those really random? Of course they are not. We don't have the computing capacity to make totally random numbers. Nobody has. Ever. All right. So B would be another random number. Then we actually start thinking of, okay, how long vector actually we need to be sure that this test actually works. I would say 100 values is already quite enough. You get, of course, a little bit more certainty if you make those these vectors longer, but not really. Not really. For this brute force test, you have one random number, another random number, 100 here, 100 there. Think of the permutations, and meaning that you will get something like the confidence of, say, at least the same as 6 sigma confidence on this brute force test. Okay, so x1 vector, random numbers, 1 row, 100 columns. 1 times 100 matrix. Same thing for the x2. There. And they are totally random. Well, as random as they can be. Good. So, next, let's calculate the left-hand side of this formula. Calculate C. We calculate this one first. Whoops. That. What I'm doing. I was trying to take this one and calculate this first. So we have the my function there. Also, let's see, left val equals my func1 a times x1 plus b times x2. This is quite simple there. That's the left hand side. Then we take the calculate the right hand side, which was that one. Right side value is my, oops, 8 times my func1 with x1 plus b times my func1. Oops, we'll change this one to capitals. B times my func1 x2. There we go. All right, and now we have two vectors there, left val and right val. Vectors. When two vectors are the same, what is the definition for the same? similarity or testing the similarity of the vectors. You calculate the distance. So basically the distance of those 2 points, or actually those could be also 2 points in a space that has 100 dimensions. The points are exactly the same if the distance is 0. Right. So calculate the distance of, and the distance actually would be left val minus right val, and we take a norm of that one home. Norm of this one would be the distance. Yes, I meant the norm of left val and right val. Answer is 0. So those are exactly the same. Yes, you have a question. Yes. Yes. I think so. Let's see. Let's see. The Boolean is a little bit. It is actually a dangerous thing since we. Oh. Ha 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 ha. So basically, we still need to use the. Those are vectors, so maybe minimum. Yeah, logical true. Okay. The Boolean operation would be basically dangerous. Even a small difference, meaning machine epsilon difference, would make those different. If you had a lot of calculations on inside of the function, that you actually start losing the computing accuracy, then you would fail with the logical, but still see the difference of say this machine epsilon. The machine epsilon is the smallest number that makes actually any difference. So anything on that range would be still 0. And actually, on the worst case, this difference would be 100 times that, and it's still 0. So 2 to the power of minus e to minus 14, actually, it's 10 to minus 14 would be still 0. So this is not science. This is engineering. Or actually, they are the same. The science, or at least the physics as a science, it's basically based on experiments. So physics is experimental science. Engineering is actually quite close to that. But nobody tells that engineering would be science, do they? Okay, science is usually useless. Right. I'm so happy that I have that one on YouTube now. Okay. No offense, man. But you can be offended if you like to. So, okay, so that was the test for linearity. Let's take a look at some other tests. So, for example, the causality. So the system is causal, not casual. You guys are more or less casual. I'm not casual. I have the, this kind of T-shirt. But causal meaning that there is a cause for the output. Practically, what it means that if you have an input where the this one is 0 for all negative n values, and then whatever when this is greater than equal to 0, then basically if you feed that one into your system, your output must also be the same, meaning that there cannot be any response of the system before the input comes. Okay. That's the causality. So the causal system does not forecast for future. Humans are not causal systems. We can actually make, thing about 5 minutes ahead of us, or maybe 1 week ahead of us. We can think of what we can make plans, but on the system, causal is kind of a dumb system that just reacts on whatever comes in. Okay. So let's see what that one would be in MATLAB. Okay. So causality. So if input starts at n equals 0, the output cannot start before. Well, yeah. So output cannot start before input. Okay, so causality. We have the function 2 times x. I already know it's causal, but just for fun, let's make a test similar to the linearity test, a brute force test that gives us a value. And for that one, it's actually, this one states that, okay, and this index actually what we need to take a look, closer look. So we start by creating index vector. So let me do 1 to 100, but then why not to change it so that actually starts somewhere at the middle. 1 to 100 gives you 100 data points, the same amount as in our x. Okay, maybe I will actually do it also like this, so I can also take the x1 and check what is the length, and now I have that index vector from minus 49 to whatever, the same number of elements as in x1. There. So that's the my n. Then I will make my x3, which is simply x1 dot times the well, yeah, I'll do some funny stuff. Oh, wait a minute. I can also do it. No, I'm not doing it that way. So dot times and n greater than equal to 0. Yeah, just in case. Might be a good idea sometimes to do graphics to see if we actually have the signal as it should be. Yeah, that looks good, test vector. So basically, then we test if our system gives also zeros before the index 0. So the system, calculate the system output. Y3 equals my func1 x3. Simply calculate it. And I can also eyeball it if this is, well, it looks like it might be a causal system since it looks like those are zeros. But since I'm not sure yet, of course I cannot be sure. I can actually calculate if that vector length is 0, meaning norm of those values where n is negative, the norm is 0. So basically y3 and the values where n is less than 0 and just calculate the norm. So this is testing if the first those values are all 0, and yes they are. And the same warning about this one, if you have big calculations on your system, it might still give you machine epsilon there instead of 0. Okay, so that was a causality. Time shift invariance. Invariance meaning that it does not change due to time shift. So basically, if we have an x in input, or if we have a delayed input to system f, and that one would be so basically if a system is time shift invariant, it means that it doesn't make any difference if we delay the input signal or delay the output signal of the system. It's still the same. And basically, if it's not the same, then usually the system somehow uses the time as an internal parameter. For example, the parking meters, 2-hour parking or 50-minute parking machines on the city center of Madrid, for 2 hours usually. Isn't it nice that actually after, say, 7 p.m., you don't need to go there, every 2 hours to put more coins. You would get a little bit too less sleep that way. So basically, the time shift invariance, well, it's not the case of if the system is good or bad, but it's just a property. Same as with the linearity. There's plenty of nonlinear systems that are absolutely wonderful. For example, cutting the high or low levels of the signals is required in order to not break your ears when you are listening music. So if you get distortion on your music, it means that it's good. Well, depending, of course, if you get the distortion in your ear, then it might be too late. But those are just properties of the signal, just like the time shift invariance. Okay, now basically what we need to do on MATLAB is how to make that delay. And for that one, let's see, let's just type help delay. Does it have? Yeah, it doesn't. So basically we use a little bit of information that comes later on today. So the implementation of delay would be filter with parameters. You have zeros, as many as needed. So you basically have n zeros for a nth order delay, and then the last parameter 1, then another one here just for fun, and then you have the input signal. So this is how you do a delay in MATLAB. Sometimes you actually need the need advanced operation, meaning, well, if this one is z to minus n, sometimes you need also z to plus n, or advanced operation a. Computationally that doesn't make any sense, but sometimes it's really useful to actually put this one on a inside of the system, just to simplify the flow diagram. Okay, advanced operation, you basically need the following parts. First, you have a part which makes n to minus n, meaning swapping the time. Then you need the delay, and then swap the time again. Yeah, that's the easiest way of doing it. Okay. Yeah, so there. I have some trouble on camera. I need a better camera stand. Okay, so time shift invariance. It is invariant if you can change the order of delay and the function. If not, then it is not time shift invariance, which is double negation, double negative kind of thing. Okay, let's take a quick look how to do it on MATLAB. There. So time shift invariance. Delay the input and see if the output delays the same amount. Okay, so I have that x3 already there. Now I will just make some arbitrary number for the delay. For example, maybe 3-point delay. So delayed signal x3d equals filter 0, 0, 0, 1. So that's a 3-point delay and x3. So, okay, that's the input signal delayed. There we go. And basically then we calculate the output. So Y3 for delayed signal, okay. Y3 for Y3 for X3D. Haha. So that is simply my func1 and X3D. There we go. Whoa, shrunk. My func. There we go. Then we calculate the output without the delay and delay that output. Then the X3, we have already calculated that one, so it was the Y3, right? But okay, let me make it this. So it's the delayed output for original signal. Okay. Okay, Y3. That was the Y3, but now we delayed. Delay 3 filter 0, 0, 0, 1, 1, my func X3. Yep. There. And then we test if those are the same. Okay, so norm Y3D3 minus Y3 for X3D. Okay. Yes. And norm is 0. That is supposed to be. It just multiplies the signal by 2. It doesn't do. It doesn't have anything to do with the time. Okay. So that means that our system was time shift invariant. If not, this value would be remarkably different from 0. Okay. Next, a little bit about the okay, that was time shift invariance. So a little bit about the systems. You're familiar with the flowcharts, right? Signal flowcharts like that. How to read the flowchart? Let me, for example, start from a simple system which is defined by difference equation. Just a moment. Yes, difference equation yn equals, for example, 0 half of xn plus xn minus 1 plus half of xn minus 2. Then I have plus half of y of n minus 1/4 of y of not n minus 1. So feedback term. So basically this is the feedback. Feedback term for the system. So the corresponding difference, the corresponding flow chart could be, for example, so that you start with the x, then you have these delays, and then you have the multipliers. Here, this one has multiplier of 1, that has a multiplier of half again. Okay. And then somewhere in here you have the output yn, and actually yn is same as, okay, these are here summed to something else. So at least there's some here, and then basically it has a couple of feedback terms. And the weight value is 1/4, 1/2, and then, whoops, this is a bit messy. Okay, so that flow diagram actually would follow this difference equation. So we can actually test it. The way actually to produce a difference equation from flow diagram, signal flow diagram, is that you just start following the signal. So you have xn here. When you delay xn minus 1, you delay that one, you have xn minus 2. Same thing for the output. In this point you have yn minus 1. Here you have yn minus 2. Very simple. Then you just have the multipliers here. So that's half times xn, okay? And here we have just the same xn minus 1. Here we have half of xn minus 2. Similarly, 1/4 yn minus 2, whoops. And here we have half of yn minus 1. Okay, so we start summing these. So this term plus this term is that one and that one. Whoa, a sign error, nobody noticed. That one is actually minus. Not the same. So minus. And then you continue adding stuff, those, and at the end, this and that would give you that, and you have the output. All right. Good. Simple way of finding the difference equation on this form. However, that's not quite enough yet. Since the MATLAB has, or basically any system for digital signal processing, you don't actually use this difference equation. You use more generic form of a difference equation. I hope I did. Did I take the picture? Yes. Okay. So what you would actually do is a generic form of difference equation. So from this, you form that you have all the y terms on in the left-hand side and x terms on the right-hand side. There's a good reason for that. Yn minus, okay, see, when I move this one, plus half times yn minus 1 to the other side, all right. And even if I warned you about this sign error possibility, someone of you will make this sign error. It has always happened. So every fifth student make a sign error on this exercise. Please prove me wrong. Okay, that minus goes to plus on the other side. Yn minus 2 equals, and then these values will be just xn plus x minus 1 plus half of x n minus 2. Okay, now I can actually formulate this one to way that helps you to define the system parameters for MATLAB, saying that, okay, this is same as the k starts from 0 to n, a k times y n minus k equals k starts from 0 to n, b k x n minus k, meaning same as, okay, ak. Here we have a0 times yn, meaning a0 is what? What is the numeric value for a0? 1. So a0 is almost always 1. Remember that one. That's a1. This one is a2. Same thing here. b0, b1. It's 1 times, okay, and b2. Ha! Which means that we can simplify the whole system and just take those values as the system coefficients. So this one is actually a vector of a0, a1, a2. And those values will be b0, b1, b2. Those are the system coefficients or filter parameters, or system parameters, whatever you like, or the coefficient vectors. Okay, for this example, we would have this vector is 1 minus half 1 over 4, and that one is half 1 and half. And very simple to do sign error in here. Now you have been warned. Okay. So that's more useful. See, now we can actually start playing around with the system. For example, that filter command takes parameters b and a and the input x in that order. Okay. It's also very simple to mix these A and B. Remember, A is the output coefficients and B are actually the input coefficients. Why that way? For historical reasons. Okay, so filter. Earlier we had a filter which has the 0, 0, 0, 1 was the B, and then the A was just 1. All right, so it means that, where did I lose my green pen here? So the delay, 3 time step delay, we had, okay, on the left hand side I have 1 times y of n, okay? One times y of n equals 0 times xn, 0 times xn minus 1 plus 0 times xn minus 3 plus 1 times xn minus 3. So yes, it is a 3 time step delay. So after you have been able to define these system coefficients, you can already use those coefficients to manipulate data. But that's not all yet. Let's continue a little bit of that. And take the, okay, now hold your seats. We take the Z transform of the both sides. Ouch. Z transforming the whole thing. Z transform is linear. And there's also the time shift operation for the Z transform. Right. So we get Z transform of, well, maybe I should just continue like this. Z transform of that equals Z transform of that. Yeah. It's a uniform and linear, well, it's uniform the function, which means that the transformation can be done that way, and linearity of this operation actually means that we can break up the sum and take the coefficients outside. So this is the same as AK times Z transform of y n minus k equals k from 0 to n bk times z x n minus k. Then we use some mathematicians' invention about z to anything n minus k. Actually, this part will be just z to minus k times z transform of x of n. So that's the time shift operation. Same thing on the left hand side, we still have the sum k from 0 to n, a k times z to minus k times z to y, z of y n. Okay, and now again linearity, or actually these are the same for every single term. So basically, we have an equation like that. And h of z is y of z divided by x of z. So the transfer function of a system is same as the z transform of output divided by z transform of input. So what we get here is simply from k from 0 to n. Okay, see which one remains on the top, bk. So basically that one goes downstairs. Y over z. Yes, you have a question. Yeah. Yes, of course. Yes, thank you. Yep. And here we have bk times z2 minus k, and k from 0 to n, ak times z2 minus k. Okay. So we have the same parameters as on our difference equation, also define the transfer function. You don't need any other parameters or system coefficients than A and B for linear time invariant systems. Good. That was fun. Ha! Was it fun or not? At least I have fun. So now we can actually continue a little bit further. Since we just magically transformed into frequency space now. Or Z transformed into frequency space. Our transfer function, I'll just repeat it here so I can have some more room. Sum of k from 0 to n, bk times z2 minus k, k from 0 to n, ak times z2 minus k. Okay, now if you want to know the zeros and poles of the system, meaning the special points for the numerator and denominator polynomial, first thing what you would do is to basically multiply both sides with the z to n to make it positive exponential polynomials. So we can just do it like that. So we multiply it by number 1, which is z to n divided by z to n. So we have the b0 times z to n plus b1 times z to n minus 1 plus and so on plus bn. Downstairs a0 times z to n plus a1 times z to n minus n minus 1 plus and so on an. And now both of the numerator and denominator are positive exponential polynomials. Numerator polynomial, denominator polynomial, nth degree, meaning that there are actually n roots on both of them. So the zeros of the system are the same as the roots of this polynomial. And that actually have how many roots? N. Exactly N. So these are complex numbers. So N roots. Good. And poles, same thing, but with the A0 and so on. And that also have a root, N roots. Okay. For the minimum delay system. But on the other hand, remember, any of these the numbers here or coefficients can also be 0. So sometimes they are not just marked there. But anyway, so we have n roots, which means that we can also define the h of z using the roots instead of the this kind of sum. So we can define it also by, well, we have the gain factor a b0 divided by a0, and then we have the z minus z1 divided by z minus p1. So basically this not so this is z vector is z1, z2, and so on. Here we have poles p equals p1, pn. Okay, that kind of vectors, and then you have c minus g2, and so on. So basically, it's a product form. Product from 1 to n of z minus zk divided by product from 1 to n of z minus pk. Good. So now we actually introduce a couple of new things there. So we have for any transfer function, nth order transfer function, we have n times n roots for numerator and denominator, meaning n zeros and n poles. Okay. Yes. Huh? Yeah, yes. N roots, meaning from 1 to n. We have, the 0th order term here, which means you have one more coefficient than you have the roots. For third order system, you have 4 the coefficients. Okay. Roots, and what can we do with the roots? Okay, I think what we can do at least is to plot the 0 pole plot. Did we have that one on? Yes, zeros and poles. So meaning if you start plotting, you would do the Argand diagram with gain B0 divided by A0. So, okay, 0 pole plot versus Argand diagram. Same thing, except on the Argand diagram, you would also mark the gain, the total gain of the system, nothing else. And you can call them 0 pole plots instead of Argand diagram. But anyways, the common way of marking is that these, you will mark zeros with circles. I'll just put them here. second order system, for example, or third order. Okay, so you have exactly the same number there. If you have a so basically you have the complex conjugate pairs or single. If you have a single pole or zero, it must be on the real axis. And then you have the poles marked, for example, something like that. And again, if you have the single pole, it must be on the unit circle. The real axis, not the unit circle. Sorry. For example, it can be on the origin. And now I can tell you something about the stability. Bounded input, bounded output stability. So system is stable if all poles are inside of unit circle. So this is the stability test, all you need to know. Critically stable system would have a pole exactly on the unit circle, meaning it oscillates on that angle. If it's outside, it's bound to actually at some point saturate. It's just due to the too high positive feedback, the signal is just increasing and increasing. At some point, you get the maximum number you can handle. Okay, so stability is actually a good property. So the other properties, linearity, time shift, and invariance, causality are just properties. Stability is good property. All right. So, yeah, I think now we have all the tools on all the theory kind of things. But this is not really. I don't count this as theory. It's just, you know, formulas and some drawings. Good. So let's take a quick look on then how to actually handle the system. So determine the difference equation for the following system, and on that one you would just write the coefficients. But I had a nice system already here. Let me go and take it from somewhere. Drive. Okay. Let me try to find the okay. So I had a system already. So following that one, I have the system parameters for my first system. Okay, BBAA. BB is half, 1, half, and then AA was 1 minus half, 1/4. Right. Not too many mistakes in that. Good. So what to do with on the system on the MATLAB then? So we can actually define the system coefficients. Just a moment. Maybe I'll just repeat the. So the system was yn equals half of x of n plus x of n minus 1 plus half of x of n minus 2 plus half of yn minus 1 minus 1/4 of yn minus 2. And the system coefficients are those. And this is the nth time I'm reminding about the possibility of the sign error. Okay. Be aware of the sign error. So the B values are very simple, just 0.5, 1, and 0.5. By the way, if you had a value missing from here, so if you didn't have, for example, the first order feedback, then this value would be 0. You don't leave any numbers out. They can be 0. Okay, so that's the coefficients for the input, and then coefficients for the output and feedback. A0 is almost always 1. Then you have minus 0.5 and 0.25. Okay, those are the values. And then we can do some magic. Let me see what kind of magic I want to do. System coefficients, calculate zeros and poles. Okay, so we can do it by, for example, calculating the roots of polynomial which are defined by polynomial coefficients b. Yeah. So we have a double 0 at point minus 1. Same thing for roots of AA. Okay. And that already starts telling me this system looks like it's also stable because of, I think, not norm, but absolute value of the roots. Yes, that's less than 1, meaning it's inside of the unit circle. Or we can actually just plot them. Z-plane BA. Oops. Huh. Huh? Why not have a Z-plane? Do you have a C-plane on your MATLAB? Try Z-plane BA. Yes, it plots. Yeah, I have broken my Z-plane. Wait a minute. B, A. Okay, I know what it is about. I have different function sets for some reason. But anyways, you got the plot. Excellent. I'm just thinking, how do I plot the same thing? I have the z equals roots of b and a equals roots of a. There. What? What did I do? Not that one. P equals roots of a, and then I can plot those on. Yes, I can. Yes, I can. Did everyone got the z-plane working? Good. You know that it looks like that. Okay, I'm not going to fix it today. I have the my own written function for z-plane somewhere, but it takes about 5 minutes to make the plotting routine, so it looks nice. Anyways, you have the routine there. Excellent, wonderful. I also should have it, but I have a feeling that this MATLAB license, what I'm using, does not necessarily have been updated for a while. All right. Or I can just try declaring the function, see what happens. No. Nope, no z-plane for me. But anyways, you got the z-plane working, and you can also already say from the plot that the poles are inside of the unit circle. Fine, good. But see, z and p. Okay, I can draw it here. I have a z-plane. I have the perfect plotting routine for that one. Real part, imaginary part. I have double zero here. That's how you mark double zero. Then there's the poles at positive side 0.25 and then about 0.433. So I have one pole here, another pole here. Okay, it wasn't that bad. Just for fun, let me modify a little bit of this system. This is kind of thing that we will probably do also tomorrow. But anyways, I will, since I kind of hate double anything. I'm that kind of guy. So let me move these poles, for example, not poles, but the zeros in those locations. So that would be 3/4 pi angle. So instead of that, I will make those locations as my 0 points and see what that one does for the system. So actually, it will be widening the stop and attenuation. I'll show that one tomorrow. But anyways, that will be a little bit better system as a filter. So modifying by moving the zeros. All right, so I can make the new zero place ZZN equals on the unit circle, meaning on place j and minus j. So complex conjugate pair times 3 divided by 4 times pi. Okay. Yeah. So that's how you generate those new zero locations. And now when we have the zero locations, we can always do the reverse function of the roots, which is pole. Not pole, the poly, yes. So my new BB is actually the polynomial which is defined by those new zero points, and now we have basically system with those values. So basically I didn't change that much. The original, let's see, original had the multipliers half, 1, half. Now I have 1, 1.4, 1/4. Okay, so square root of 2, 1, or half 1 over square root of 2. No, let's see, half divided, yes. So half 1 over square root of 2 and half. So only one term actually changed here. When you're doing the polynomial coefficients from the this special locations, the roots, then you always are missing the gain factor, total gain factor. So that's why you always get the first term from this poly function will be 1. Highest order polynomial coefficients from when you don't have the gain information will be 1. Okay, but anyways, so now I have a modified system. And then of course, how to use the system. I still have the x3, I think, or x some values there. Let me see what the system does for the signal. Modified system does for the signal. So we have the x3, something like that. x3, yes. We started at 0 position, yes. So I can calculate the y3f. So this is the function. I use the filter with coefficients bbn, aa, and then x3. There. Let's stem a couple of things. First, the x3. The input looks like this one here. Whoops. Whoa, yeah, that's a big one. Then on another big figure, new figure, and then I'll calculate, stem. Figure, and then I stem NN and Y3F. Where's the picture? input signal and output signal. There are some similarities, but also something different. So first of all, it looks like we have some sort of scaling property on that signal. So on the output, so the output maximum are about 2 times bigger than the input maximum, 2.5, something like that. So the system is not unity gain. But anyways, you can also see that there's a lot of variability in the input signal, but not that much on the output signal. The output signal is actually changing a little bit smoother. So I would say that this system is a low-pass filter, but you knew it already, right? You should have knew though. But anyways, I'm so proud I could make it just a low-pass filter, just like that. Okay, so let me take a quick look again here. So today's exercise. First, you have the linearity check, meaning you will write those functions 1, 2, 3, 4 for yourself and run the system linearity check, then the causality check, and then the time shift invariance check. Check. Then determine the difference equation for the following system. So basically, reading the flowchart and writing the difference equation on this form, normal form, so to speak, but then system parameters B and A. What are the system parameters B and A? And be careful. Two of the most common mistakes are done on this exercise. Okay. Sign, and then the other one is mixing the A and B coefficients. 6, calculate zeros and poles and determine is the system stable. So draw zeros and poles on the Argand's diagram, meaning the z-plane in your system. And see, there's also the question. One hint, if you get unstable system, then you probably have either sign error or the mixed or the B and A parameters. And then we change the system for this one. What are the parameters? And then zeros and poles. Is the system stable? Then again, generating the sound sample. And now we have random noise with amplitude, not signal to noise ratio, but amplitude. RMS amplitude of that. And then use the previous signal for the system equation 2.7. Compare input output and observe how the system modifies the signal. Oh, right. That is today's exercise. Any questions? If not, then you probably want to start working on the exercises. Finish the exercise 1 first and then continue on the other one. Okay.